So we are continuing on the mechanical properties of materials, and now we will be looking at the elastic and plastic type of deformation that we observe in materials, and then we will be looking into some ideal material behavior. Now, in our last video, we have seen the uniaxial tensile testing of a steel rebar, and we have learned that from the loads and deformations that we obtain during such testing, we can draw the stress-strain diagram of a steel rebar, which is basically a mechanical property of the steel rebar. So if we were to look at the basic deformation types that we observe in load-carrying materials, we can divide them into three. First of all, elastic deformations, and we call those deformations that are instantaneous and instantaneously again recoverable. Another type of deformation is called plastic deformations, and those are also known as non-recoverable deformations. And these two types of deformations we have observed in that steel rebar testing. But for some materials, we can observe another type of deformation, which is called viscous deformation, and their characteristic property is that they are time-dependent deformations. If I were to explain these deformations types through some schematic drawings, let's take this rod that will be subjected to tension, so uniaxial tension test. But if we were to look at the inside of this rod, we will see these atoms or ions or whatever you call them. Now, if we are loading this rod by pulling that from the bottom, so this is uniaxial tensile testing again, what we will realize is that these atoms or ions will be stretched as the force increases, or as the stress increases, there will be some deformations that will be observed in these ions or atoms. And that type of deformation is elastic, and as soon as you unload that material, the material will return back to its original shape. So the atoms or ions will return back to its original shape. And if you were to plot this force deformation diagram, as the load increases, this deformation will continually increase. But as soon as you remove that load, the deformations will be recoverable. And then this is so-called a linear elastic behavior. Sometimes we can have a nonlinear elastic deformation as well. And this time, the deformation will not be linear, but it will be, again, recoverable. So don't forget, elastic means reversible or recoverable. And it can be observed like in brittle ceramics that are subjected to compression like this. And as you can see, as the stress increased like to the order of 300 megapascals, there will be a linear elastic deformation on that brittle ceramic. Now, another type of deformation will be plastic deformation. And I will again try to explain this through this schematic drawings. Again, I am applying a uniaxial tensile load to this material. So up to a certain load that I will call Fy, or the yielding force, what will happen is that the bonds stretched up to this load, and just like what we have seen previously, the deformation will be elastic. Now, if you were to increase this load, the deformations will continue, but in a different way. And it will be difficult for me to show them on here, but I will so therefore take a replicate of that. But what will happen is that as the load increases, sometimes these atoms will slide down or will shear, what we call, on a certain plane, on a certain or along a certain direction. And if you were to continue increasing that load, what will happen is that that shearing will further continue. So this type of a deformation is called a plastic deformation, and the deformations will take place along these shearing planes. So this is a plastic deformation. So what's the difference? When you unload it, now let's look at what's going to happen. Well, what's going to happen is that that stretched bonds will return back to its original shape, but the planes will remain sheared. So the elastic deformations will be recovered, but the plastic deformation that you observe over here is non-recoverable. So if you were to plot a force deformation plot for this type of a material, what will happen is that as the load increases, there will be an linear elastic behavior as we have just seen. But once you reach this yielding force, the deformations will continually increase along these shearing planes, and it will continue. Whenever we unload now, see some of the deformation that are elastic will be recovered, but the plastic deformations will not be recovered. So plastic means irreversible or permanent. So we can observe such behavior in ductile metals. As you can see, we have an elastic behavior and then a plastic behavior. Or we can observe them in ductile polymers, again an elastic behavior and a plastic type of behavior. Please note that the strains that we observe in ductile metals versus ductile polymers are quite different. The ductile polymers will deform a lot, basically. Well, this video is obtained by Professor Göktepe. As you can see, there is some plastic deformation that takes place. This is a polycarbonate that is being tested in uniaxial tension. And as you can see, elastic deformations increase up to a point, and then plastic deformations took place. The third deformation type that we observe in some materials, are viscous deformations. And plastic deformations in non-crystalline solids, or as well as liquids, occur by this what's called viscous flow mechanism. This is in fact mostly attributed to fluids, but solids may also behave like viscous materials under high temperature and pressure. But some solids, like non-crystalline solids, do not need that high temperature and pressure for viscous behavior. And viscous materials deform continuously under stress. So whenever there is some stress, viscous deformations will take place. And their most characteristic behavior is that they are time-dependent deformations. I will try to show you the third deformation type, the viscous deformation, through 3 videos that I have obtained from Professor Göktepe. Over here you have an elastomer that is being subjected to a shearing load. So the load is applied like that. And if you were to apply this load slowly, this is how that material deform, versus if you were to test it fast, this is how it will deform. As you can see, there is a difference in the amount of deformation that you obtain. In the slow loading case, at the same load, you can have larger deformations when compared to a fast loading case. So this is a characteristic behavior of viscous deformation where the deformations are time dependent. Let me turn my pointer on again. Now, based on these above mentioned three deformation types, we can make several material idealizations. So we can make several ideal material behavior. First, ideal linear elastic material, ideal plastic material, and ideal elastoplastic material. I will try to briefly explain those now. In an linear elastic material behavior, so if you are subjecting a material that is unknown over here, and if you pull it, if you obtain such a stress strain diagram, this is called a linear elastic material. And linear elastic materials undergo deformations as subject to the loading, and upon removal of the loading, they immediately recover their original shape. So we don't observe any permanent deformation. So this is an ideal material. The second ideal material is plastic, rigid materials. So as you can see, if you are testing a material, if you are subjecting to load deformation and you obtain stress strain diagrams, as you can see over here, there is no deformation up to a certain load. Remember, this is an ideal material. And once you reach a certain stress level, the material will continually increase in strains. And once you remove the load, you will obtain a perfect plastic strain. So such materials are called plastic materials or perfect plastic or rigid materials. So in this case, as I explained, these materials do not exhibit any deformation up to a certain stress threshold, which what we call yield stress. But once you reach that, permanent deformations, permanent strains will take place. The third ideal material behavior will be a combination of the first two, and named as elastoplastic. So elastic and plastic material behavior combined. And as you can see in this schematic drawing, first, as the stress increases, the strains increase linearly up to a certain threshold, what we call yield stress. Once you reach that, deformations will steadily increase. And upon removal of the load, the strains will be partly recovered, and these two slopes are equal to each other. So, in elastoplastic materials, they deform elastically up to a limit, and within this limit, you are loading it. If you were to unload over here, what will happen? Well, it will return back to its original shape. So within this limit, if the load is removed, the material returns to its original shape. But if the load passes the elastic limit, so over here, plastic deformations will take place. And upon unloading, the elastic part is recovered, leaving us the plastic deformations. So this concludes our second video. And in the next video, we will be looking at the elastic material behavior, and we will be learning a term called modulus of elasticity.